We are going to change the conversation a little bit and talk about complex numbers. If you remember in Algebra 2, a complex number was something that could be written in the form a plus bi. And sometimes we called it z, gave it a name. So z is a plus bi. We had a real part and we had an imaginary part. I, if you remember, is the square root of -1. And you spent a lot of time finding powers of I where I squared is in fact -1. So we're leaving the realm of really what we've spoken about before because we're talking about a different set of numbers. The other thing you know is that any real number that you know, say 3, could be rewritten as a complex number. 3 plus 0i. You could have 3 plus 2i. You could have 0 plus 2i. And the latter is a purely imaginary number. Purely imaginary. And what we did in Algebra 2, which seemed a little bit silly, was we plotted these. Really just because a complex number has two parts to it, a real part and an imaginary part. And when you plot an ordered pair, well, that has two parts, so we might as well kind of use one for the other. So the x-axis we called the real axis, and the y-axis we called the imaginary axis. And you would basically just plot the coefficients. So 3 plus 0i is really at the ordered pair, 3, 0. 3 plus 2i is really the ordered pair, 3, 2. And 0 plus 2i is the ordered pair, 0, 2. And the other thing we would talk about is something called the magnitude. So if z is 3 plus 2i, if we wanted to talk about the magnitude of z, sometimes, in fact, you use a double bar to talk about magnitude. That gets into vectors. Sometimes we just talk about absolute value. But it's not really the absolute value. It's not really the absolute value. It's the distance from the origin. It's unfortunate that we use the same notation. There were similarities, but it's the distance from the origin. And you know the distance from the origin we would get by using Pythagorean theorem. So the magnitude of this number z, 3 plus 2i here, is just the square root of 13. Now, you might be noticing that the magnitude, the distance from the origin, is the same as what we would call r in polar coordinates. And in fact, that's what we're really going to talk about. When we have a complex number, in fact, plotted, we would like to write it in polar form because it will always have an r and it will always have a theta. And we have a specific way of doing this. So I'm going to start with one example. I'm going to take one complex number and show you how we write this in polar form for a very good reason. Let's take the complex number 1 plus i. And if we were going to plot it, that would be kind of easy. You know, we go over 1, up 1. Here it is, right over here, right? At the ordered pair 1, 1. And we know, because we know a lot about this, that our r value is square root of 2. And we know our theta value is pi over 4. Now, rather than write this as an ordered pair, if I was going to write it as an ordered pair, I'd write my polar ordered pair just like this. But what I'm going to do is I'm going to replace this with, I'm going to use the formula r cosine theta, right? That's my x value. So I'm going to say that this is going to be square root of 2 times cosine of pi over 4. And the coefficient of the I term over here again is 1, but I know that that means my y value is 1, and I'm going to write this as plus square root of 2 times sine pi over 4 all times I. So 1 plus I, so this is rectangular form, gets rewritten in polar form as square root of 2. I'm going to factor that out. I'm going to have cosine pi over 4 plus I times the sine of pi over 4. And what we're doing is highlighting the two important parts that are going to be of use to us very shortly. And in fact, if I get lazy, I can write it as square root of 2, and I'm going to call this cis pi over 4. Square root of 2 cosine pi over 4 plus I sine pi over 4. So it's always something like that.